Hi everyone, I'm Melanie.
And I'm Samantha.
And today we'll be doing a chi-square project in which we calculate the chi-square value of the colors we receive in a M&M fun size pack. So what is chi-square and what does it represent?
First of all, chi-square is an equation which is commonly used in science to see if the data we observe, which is represented by O, is in an experiment, is the same as or similar to what we can predict in the experiment, or the expected value, which is represented by E, according to its statistics. By calculating chi-square, we can identify whether or not the outcome of our observes are due to the randomness, or if the results are influenced by other forces. For instance, if the observed data is much higher than the critical value of the expected outcome, which can be found from the chi-square chart, that means that the data from what is expected and the data from what we observed is very different from each other. This would suggest that there were other unpredicted factors that have changed the results from the expected value.
So to begin, we will get our materials and set them up. For this experiment, we will need paper, a paper towel, M&Ms, a calculator, and a pencil. So very briefly, let's go over the procedures of this lab.
First of all, we have to open the M&M pack and divide each individual piece group with matching colors. We would then have to identify the expected value of each color, which is drawn from the total number of M&Ms in the pack. Next, we would plug in the data into the chi-square equation and solve. Afterward, we would need to find our critical value from the chi-square chart and compare it to the number we calculated for the chi-square value.
So before we begin, let's present our hypothesis that we created for this experiment. So our first hypothesis that we created is if the chi-square value of the colors of the M&Ms are less than or equal to the critical value of 0.05, then our batch can be accepted and sent to market because we can be 95% confident that there's not a significant difference between the observed data and the expected value. This will imply that there's no outside force changing the observed data from what is expected.
To test our hypothesis, we created a null hypothesis, which is if the chi-square value of the colors of M&Ms are greater than the critical value, then we should reject the batch since there may be a significant difference between the expected outcome and the observed outcome. The first step to this experiment is to open our pack of M&Ms and divide every individual piece into groups based on their color. In this case, we have 3 blue, 2 orange, 1 green, 1 yellow, 1 brown, and 0 red.
The data we record will be used to calculate the chi-square value, but before we calculate the chi-square of the M&M colors, we have to calculate the expected value of the expected outcome first. The number of M&Ms may vary depending on the pack one pulls. For instance, someone can open a bag and only have 6 pieces of M&Ms, but the next person can easily pull 7, 8, or 9 M&Ms from that bag. So this means that calculating the expected number of each color of M&Ms may be different for every person doing this experiment. So to find the expected value, we would first have to take the percentage of the expected colors that were calculated from the M&M factory. According to the M&M factory, the expected percentage for both the blue and orange M&Ms are 20% for each color. And for green and yellow, it would be 15% for each color. And finally, for red and brown, it would be 12% for each of the colors. So to find the expected value, we will have to take the expected percentage for each color and multiply for the total M&Ms we received. So in this case, we received 8 M&Ms for this pack, and for blue and orange, we will multiply 8 by 23%. For green and yellow, we will multiply by 15%, and for red and orange, we will multiply by 12%. So to find the expected value, we will have to take the expected percentage of each color and multiply it by the total number of M&Ms received. This would tell us how much of each color that we are supposed to receive in one M&M pack. So for the blue and oranges, we have an expected value of 23%. So we will multiply 8 by 0.3, which is 1.84. We would then have to repeat this step for the rest of the colors. So for green and yellow, we will multiply 8 by the expected percentage, which is 0.15, which equals to 1.2. For red and brown, we will multiply 8 by 0.12, since that is the expected outcome for those two colors, which would be 0.96.
After finding our expected value, We will now be subtracting our observed by our expected. In our case, we got 1.16 for blue, 0.16 for orange. Now we subtract the rest of them. We will now be focusing on O minus E squared. With a difference from the previous problem, we will now be squaring every single one of them. For our blue, we got 1.35, and for orange, we got 0.03. We will continue doing this until all of them are squared. Here's all of them finished. With the square differences, we will now be dividing them by the expected. For blue, we'll be dividing 1.35 over 1.84. And for orange, we'll be dividing 0.3 divided by 1.84. I'll first be writing down the numbers on the left divided by the expected. Then I will find the answers to all of them. For blue, we got 0.73. For orange, we got 0.016. And green, we got 0.03. I will now be doing the same to the rest of them. Finally, we will add the numbers on the left all together to find our chi-square value, which is 1.7677, which we rounded to 1.77. Now that we have found the chi-square value of the M&M pack, we will find the critical value, which will be used to compare the chi-square value. The chi-square value, or the probability of a random chance occurring, has already been calculated and recorded by experts. To find the critical value, we have to find both the p-value and the degrees of freedom, which is an estimate number of independent pieces.
So firstly, let's identify the p-value. So most scientists use the p-value of 0.05 because it gives a 95% confidence that the probability that the data is within the expected range. So we will be using the p-value of 0.5 like other scientists. Secondly, we need to find the degrees of freedom, which is calculated by subtracting the number of colors we are calculating by 1, since the colors are the subject that we are calculating. So since 6 minus 1 is 5, our degrees of freedom will be 5. The critical value that we will use to compare to the chi-square value that we calculated will be the number found at the intersection of the p-value we chose, which is this one, and the degrees of freedom we calculated, which is this one. And that means that our critical value for this experiment is 11.07.
Since our chi-square value of 1.77 is less than the critical value of 11.07, that means that our observed data falls into the expected value and we can reject the null hypothesis. This is because the critical value is a close estimate that suggests that factors other than randomness are affecting the observed data. Anything larger than the critical value would mean that the observed data is more different than the expected data. Since our chi-square value is less than the critical value, then we can be at least 95% confident that our observed data falls in line with the expected data, meaning that there are no other factors that can change the abundance of colors we see in the M&M's pack we opened.
So therefore, we can accept our hypothesis, which is if the chi-square value of the colors of M&Ms are less than or equal to the critical value of 0.05, then the batch can be accepted and sent to the market because we can be 95% confident that there's not a significant difference between the observed data and the expected value. So moving on, let's talk about experimental errors. So despite this experiment or this lab seeming to be so simple, there can actually be a few experimental errors done throughout this experiment, causing the results to be different. For instance, while doing this experiment, it's easy to mess up on the math. There could be a simple misclick on the calculator, which we've done multiple times, and this could change the results of the entire experiment.
In addition, it can be very easy to mistake E, the expected data, for O, the observed data, or vice versa. Be sure not to divide the O minus E squared by the observed data like we initially did. So in conclusion, based on what we observed, the data that we collected matches with the expected percentage of colors from the M&M factory. This means that the colors that we received from this M&M fun size pack is mainly contributed to randomness of dividing the colors, rather than other unforeseen forces.
So thank you so much for watching this video. We hope you like it. And please feel free to like and share this video with your friends so that they can learn more about chi-square. And that's it for us today. Bye!